So, hello everyone. My name is Claudia, and I'm going to present the work Ionized gas winds from the nucleus of OH megamaser galaxy IRAS 09320 plus 6134. So, ultraluminous infrared galaxies are, or just ULIRGs, are a class of galaxies among the brightest objects in the universe, showing luminosities in the infrared above 10 to the power of 12 solar luminosities. These environments consist typically of galaxy interactions or mergers, and they are believed to represent a key step in the processes of transformation and evolution of galaxies. The extreme luminosity in the infrared may be associated with intense star formation and/or the presence of an active galaxy nucleus, or an AGN. So a maser, similar to a laser, is a microwave amplification by stimulated emission of radiation. Megamasers then are luminous and powerful extragalactic masers with luminosities on the order of 110,000 solar luminosities. They have that name because amplified spectral line is due to a transition in the hydroxyl molecule. They are associated with merging and/or interaction environments, and many OHM host systems present composite spectrum, showing both features of starburst and AGN. A possible explanation for that is that galaxies with OHM would represent a transitional stage between starburst and AGN. The galaxy from this study is part of a sample of 15 galaxies with OH megamaser emission from a project whose general objective is to relate the properties of OHM to AGN and/or starburst activity. It is an important study to understand the nature of the ionization mechanism of the gas involved in these merged environments, and to propose a scenario that justifies the presence of megamaser emission. We performed a mapping of the distribution, kinematics, and excitation of the gas in this galaxy using integral field spectroscopy. 6 galaxies in the sample have been studied so far, and in 5 of them was detected the presence of AGNs. The galaxy IRAS 09320 plus 6134 is a ULIRG with luminosity in the infrared of 10 to the power of 12.02 solar luminosities. It has a redshift of 0.03937, which corresponds to a distance of about 176 megaparsec. The data came from Gemini Observatory that consists of 2 telescopes, one in the north hemisphere and another in the south hemisphere. In this case of this galaxy, it was observed in the Gemini North. So the data came to me not readable, so I have to make a process that I can work off then. This process is called data reduction, and it made using a software called IRAS. This process then is a multi-step process with the aim of make raw data readable for work. The data cube is the end product of data reduction, and it is literally a cube, so it has 3 dimensions, 2 spatial dimensions and 1 dimension corresponding to a range of wavelengths. Here is an image to exemplify what I say. The methodology is EFS Cube, which is a Python package, and it consists basically of two steps: the gas distribution and kinematics, and the gas excitation mechanism. The first is fitting of Gaussian curves and Gauss-Hermite series to the profiles of the emission lines present in the spectra of the galaxy. It allows us to construct two-dimensional maps of flux distributions, velocity fields, velocity dispersions, and Gauss-Hermite moments of the gas for each fitted emission line. The gas excitation mechanism is a construction of one diagnostic diagrams and allows distinction as to whether the source of ionization of the gas is due to a star-forming region and or an AGN. So here is a nuclear spectrum of the galaxy to show the lines that I work, which are those lines here, the emission lines. The results then, here are the Gauss-Hermite series results. They are kind of similar to the Gaussian curves, so I'm going to talk more about the Gaussian curves results. Here are the flux distributions results. The peak emission is in the core for all lines in both components. Here in the left is the narrow component, and on the right is the broad component. And we also can see extended emission across the entire field. And this seems to be a star-forming region, but I don't know for sure yet. The velocity fields, in the left, the narrow component appears to be tracing the emission from the galaxy's disk and show a rotation disk pattern. This blue and red here is a rotation disk pattern. The narrow component, here is the results of the velocity dispersions, and the narrow component has lower values for the entire field. And the broad component has higher values. The one diagrams for both components, most of the points are observed in the AGN region here, indicating that the ionization mechanisms of the emitting gas of both components is due to the AGN. Here, this region and this region is AGN. So the conclusions. We performed a two-dimensional mapping of the distribution, kinematics, and excitation of the gas in the central region of the OHM galaxy IRAS 09320 plus 6134. The fit by Gauss-Hermite series did not result in a representative model of the observed emission lines, indicating that the gas has more than one kinematic component. 2 Gaussians per emission line were then fitted, and this proved to be a good model of the profiles at all positions mapped in the galaxy. One of the Gaussians is narrow and the other is broad. The narrow component is tracing the emission from the galaxy's disk, and the broad component is observed predominantly internal to the galaxy's nucleus, and it is all blue shifted in relation to the narrow component. This component is interpreted as due to an outflow of ionized gas from the AGN. The one diagrams show that both the emission of gas located in the disk and the emission of gas in outflow are predominantly due to ionization of the gas by an AGN. BPT diagrams are also under analysis and seem to confirm this result. It is also intended to calculate the outflow rate in this galaxy, since understanding outflows and their effects on the host galaxy is very relevant in galaxy evolution studies. That's it. Thanks.